Okay, so thanks for coming back. So today we're going to talk about symmetric monoidal posets and enriching in them, which is some math terms, and how those correspond to things you can call resource theories and navigation. So the motivation is are these parts, the resource theories and the navigation. So a resource theory is that you come up with things that you have and things that, all the things that you can have and want. And when what you have, so the question is, given what I have, can I get what I want? That's a pretty important question people ask themselves. And so this will, right, so for example, suppose I want a lemon meringue pie. And I have these ingredients. I have crust, I have butter, I have sugar, I have eggs, etc. So I take the eggs and I say, can I get what I really want, which is egg white and egg yolk? And if you are able to separate eggs, then you can get an egg white and an egg yolk out of an egg. And if you have sugar and an egg white, you can make something called meringue. And if you have yolk and you have sugar and you have lemon, say, and butter maybe, you can make some lemon filling. And if you have crust and you have lemon filling, you can make something, some kind of filled pie, and you put the meringue on top, and now you have an unbaked pie. And so in this case, all of the wires correspond to resources you can have. You could have, someone could give you a crust resource or a butter resource. So the wires are resources. Maybe someone gives you some money, I don't know, whatever. And the boxes are, can I make the resources on the right, what I want, from what I have? So if you can make yolk and white from eggs, and you have so if you have a recipe for this one, and you have a recipe that takes egg whites and sugar and produces a meringue, and you have this recipe and this recipe and this recipe, then this gives you a recipe for the whole pie. So it converts sub-recipes into recipes. And that's what a resource theory is. It's the rules, it's kind of telling you what your resources are. In your manufacturing plant, you may not care about any of these resources. You care about screws, nails, hammers, whatever. And so you have your resource theory that is irrelevant to me as a baker. And so a resource theory is one of these kind of things. So that's the first motivation. Part is to talk about that kind of thing. And the second part of our motivation is navigation. So this resource theory will correspond to symmetric monoidal posets. This thing. And navigation will correspond to enrichment, which is based on the first one. We're going to enrich in a symmetric monoidal poset. But what do I mean by navigation? There's different kinds of questions. If you have a navigator in your car, someone sitting in the front seat navigating, they may be more or less adept at that task. But one thing they could do is they could answer questions like, can I get from A to B? You give them 2 points and they'll answer the yes/no question, can I? Or they could answer the question, these are not wires, these are blanks. Can I, how much time to get from A to B? What's the probability? That's probably not someone in your car, but it's a similar sort of question. What's the probability that I can? And what are all the ways to? Get from A to B. And so in navigation, you not only have these different sorts of questions, but you always have this kind of notion of better and worse. So being able to is better than not being able to. Taking 5 hours is better than 6 hours. Probability of 1 is better than probability of 90%. having more ways too is better than having less ways, say. Or having a subset of ways is worse than having all the ways. So you have this notion of better and worse. You have this notion of like, I don't know how to call it, daisy chaining roots, or like kind of combining roots. So if you have a root from A to B, and you have a root from B to C, you have to be able to get a root from A to C. And so this is like combining roots, or maybe waypoints. And finally, searching. So your navigator has to search. So if there's like lots of different routes from A to B, and this one's 5, 3, and 2, and this one's 7 and 4, you have to decide which route is faster. And so that's something a navigator does. So we're going to talk about navigators and enriching in what are called these monoidal posets. And that will structure the question of, if you enrich in one monoidal poset, namely the Booleans, you get the can I navigator. If you enrich in something called Lever's monoidal poset, you get how much time. If you enrich in the probability monoidal poset, you get this one. And if you enrich in something else, the category of sets, you get this one. Now the category of sets is not a poset, so it doesn't actually belong in this lecture. But it belongs with this navigation idea, and it'll come in the next lecture when we talk about categorification. So in this lecture, we'll be talking about those questions, but it's almost the same. Okay, so those are the motivations for today's talk. And we will, as usual, I'll have you guys talk amongst yourselves sometimes and make sure you understand stuff. And you can ask questions at any time. And yeah, so I'll get started. So the first thing before I have you talk a little bit is to recall. So in this part, we're talking about symmetric monoidal posets. And that's kind of a mouthful. So I might say monoidal poset, and I always mean symmetric monoidal poset. So recall that a poset is just two pieces of structure. It's a set and a relation, where you have that for all P and P, P is less than itself, and if P is less than Q and Q is less than R, then P is less than R. Okay, and we talked about Hasse diagrams last time too, or maybe the first time. And that is where you have all your elements of P. And you draw an arrow if P is less than Q. But any path, actually, if you have a path through these arrows, it means P is less than S, P is less than itself, etc. So in this one, S is not less than anything except for itself, and P is less than everything. Q is not less than R. So why don't you guys just take a few minutes? I'll give you 2 minutes to talk about amongst yourselves to make sure you understand posets well enough to continue. And just if you have any questions about all the stuff we've talked about so far, like anything you liked, didn't like, whatever about it, just say something to your neighbor and introduce yourselves and answer those questions.
Hi. I am actually which is not like this at all. We're going to only you can also do that any problem how different particles are. I don't actually know anything about and it sounds very nice and easy, but it's not particles are weird shapes.
No, they're IP, so basically
Okay. So any questions remaining from? That's awesome. Any questions remaining from that? Anyone have any residual questions or comments? Yeah.
I don't know if it was just me, but I couldn't follow like the natural transformation business that we talked about at the very end last time.
Okay, natural transformations. Okay, we won't need that today.
Okay.
Right. But you can stay after class, and I can tell you about it again, or whatever. Anyone who has any questions can stay after class, and we can talk about them. Other questions or comments? Okay, so we're going to talk about symmetric monoidal posets. So these are posets with additional stuff going on. And so I will now define what a symmetric monoidal poset is. Okay. So definition. My cameraman didn't move the camera. Sorry. Oh. So definition. So suppose you have a poset already. So you have a poset sitting there. Be a poset. A symmetric monoidal structure on P consists of some things. One, an element called I in P, or denoted I, called the unit. And two, a function called tensor, that's just the name of the function, that takes two elements of P and gives you back one element of P, called the monoidal unit, or what? Called the product, monoidal product. Okay, and these have to satisfy two rules. No, four rules actually, 4 rules. So the first rule is that if P1 is less than P2 and Q1 is less than Q2, then P1 tensor P2. So this tensor is combining. So it's going to be like combining H2O and sodium, or it's like combining crust and butter or something. So this is like, I have crust, I have butter, now I have both. It's not really combining, it's having both at the same time. So if from P you can get if from P1 you can get P2, and from Q1 you can get Q2, then the rule is that from P1 and P2 together, you can get Q1 and Q2 together. So that's rule 1, or rule A, I guess. Another one is that P tensor this unit. The unit is going to be like nothing. I have the absence of everything. I have nothing. P tensor I means if I have P and I, then I have P. Yeah.
Am I misunderstanding something, or should that be P1 tensor Q1 less than P2 tensor Q2?
Yep, thanks. Thanks. P tensor I is P. Letter C is that I tensor, no. And this is also I tensor P. C is that P tensor Q, if I have those two together and then someone comes and gives me R, that's the same thing as if I had P and then someone comes and gives me Q and R. And D is that P tensor Q, this is the symmetric part, P tensor Q equals Q tensor P. And if you have those four things, if you have these two things, these two pieces of structure, and they satisfy these four rules, then you have a symmetric monoidal structure on your poset. And if someone tells you they have a symmetric monoidal poset, they're really just telling you is a poset with a symmetric monoidal structure. So it's the structure that's the important thing. If someone gives it to you and it already has the structure sitting on top, then it's a symmetric monoidal poset. So the reason that's an important distinction is, let's give some examples of these things. So I'll give some examples and some non-examples. 0 plus. So here, what you do is you write the set, the relation, the unit, and the product. Maybe you can't read any of these words, but you kind of see how long they are, and that's like enough to kind of get. Okay, so first of all, is this a poset? Is it true that 5 is less than 5? Yes. If 5 is less than 6 and 6 is less than 9, then 5 is less than 9. Okay, it's a poset. This part is the unit. This part's the way of taking two elements of R and returning a new element of R. And I check that if A is less than, if P1 is less than P2 and Q1 is less than Q2, then P1 plus, so I'm using this here, P1 plus Q1 is less than P2 plus Q2. And that's true. Okay. And anything plus 0 is itself. And plus is associative. 5 plus 7 plus 10 is the same thing as 5 plus 7 plus 10. And finally, 5 plus 7 equals 7 plus 5. So this is an example. Another example is the natural numbers with less than and 1 and times. So natural numbers with less than is a poset. 1 times anything is itself, times is associative. If A is less than B and C is less than D, then A times C is less than B times D. And you're good. So this also works. But it actually only works because the naturals are all positive. So a non-example, someone could trick you by giving you this thing that looks kind of like a combination of these two. And that's, what axiom does it fail? Yeah.
The first one, A.
The first one, A. So what's an example? P1, P2.
Minus 10, minus 1.
Minus 10, minus 1, 0, 0. Yeah. So minus 10 is less than 0. Wait a minute. I didn't want to do it that way. Q1, P2. Minus 10 is less than 0. Minus 1 is less than 0. But this times this is not less than this times this. Okay, so that's what can go wrong. Lots of things could go wrong. But, I mean, this many things can go wrong. But this is kind of the one that you, well, I don't know, the one that goes wrong here. I guess that's all I can say. Okay. Any questions about that? So symmetric monoidal posets are the topic of today's talk. We're going to talk about wiring diagrams, which are pictures like this, and how they correspond to symmetric monoidal posets. We'll talk about many more examples, like from industry and science and from math. And we will talk about enrichment in a monoidal poset, which we'll get to this navigation thing. Okay. So this is a kind of interlude on wiring diagrams. They come in many flavors. So here's a flavor of wiring diagram. Maybe that's vanilla. I don't know. Vanilla. there's this flavor. There's this flavor. So you can have all sorts of different flavors. Right? In this one, you're only allowed to draw things in series. In this one, you're allowed to draw them in series or in parallel, and there's allowed to be feedback. In this one, you're allowed to draw circles for some reason. In this one, wires can split and merge. The thing that makes a flavor a full flavor, if you will, is that if you take any one of these pictures and insert it into one of the boxes, you get another picture. So if I insert, say, this picture into, say, that box, it would just kind of give us another wiring diagram of the same flavor. If I put one of these pictures with, so here I have a 2 input, 1 output. If I put it into any box in here that has 2 inputs and 1 output, I would get another one of this same flavor. And same with this and same with this. So when I talk about flavors of wiring diagrams, I'm talking about different kinds of monoidal categories. Like this one is not monoidal at all, just regular categories. You can compose things in series. In this one is something called hypergraph categories because they look like hypergraphs. This one might be called a compact closed category. This one might be called a category with byproducts or something, or bimonoids. These are all just words that mean I can interpret this kind of diagram. And our next goal is to say what it means to interpret a wiring diagram. So these are like things you might see. I'm not telling you what they are yet. I'm just drawing pictures right now. The next step is to tell you what they are for us. So our, I guess, flavor of the day. The one that works for monoidal posets, symmetric monoidal posets. And that flavor has pictures that look like this. So wires are allowed to cross. That's the symmetry part. You're allowed to combine things in series or in parallel. There's no feedback. Wires don't split, wires don't merge, stuff like that. So these are what our diagrams are allowed to look like today. And the next step is to try to explain where, what these different pieces mean. So suppose P with less than and I and tensor is a symmetric monoidal poset. Then wires are objects of P, elements of P. Or can be labeled with. Okay, so here we're allowed, let's say P, right, so but P is, say we're looking at the reals with 0 and plus. And you could label wires with 5 and negative 11 and pi, right? And this thing means 5 tensor negative 11. So this wire, a wire labeled 5 tensor negative 11, and this wire are the same wire, are the same thing. It's kind of like you're allowed to bundle wires and label them with the bundle name. This would be 5 tensor negative 11 tensor pi.
Question.
Yep,
What would happen if you, instead of pi there, you had a -6?
minus
And then-
6.
Yes, and then
Yep.
you tensor 5.
Yeah, so 5 tensor negative 11 in this thing is negative 6. So if
Now
you do
you've
this,
got
you'll
it
get
same.
negative 12. And maybe you meant positive 6. So then
negative
you,
11.
oops,
Oh, it's,
what
yeah,
did I do?
I think you meant -6 both ways.
What did I do? Minus 6, 6, and that's 0. Is that what you meant?
No, it isn't. I just wondered, you could get -6 in 2 ways. You could put it in. Do you have
Oh.
to identify them or?
I see.
Yeah. 'Cause-
Yes,
yeah,
they're the same.
Yeah.
Yeah. There's something called a strict monoidal poset and a lax monoidal or a weak monoidal poset, and in a weak one you wouldn't have to say they're exactly the same. You would just say that -6 is less than 5 minus 11, and -6 is greater than 5 minus 11. And so they'd be like as good as each other, but not quite exactly the same. But that's kind of a very small point, at least mathematically speaking. Okay. Right. So the iconography, or what these boxes mean, what this picture means, is the wires mean elements of your poset. So this might be P and Q and R and S and T and U and V and W. And a box, and drawing wires on top of next to each other like this is tensoring. And a box like P, Q, R, S, T, this means P tensor Q, because that's what these two wires on top of each other mean, is less than R tensor S tensor T. So boxes mean the less than relationship. And what one of these wiring diagrams means is that if you have, say, so let's see, 5 is less than 6 plus 2, and 2 plus -5 is less than 4, well, 0, and 6 plus 0 is less than 5 plus 4. Okay, so if you agree that 5 is less than 6 plus 2, and you agree that 2 plus -5 is less than or equal to 0, and you agree that 6 plus 0 is less than or equal to 5 plus 4, then this is a proof for you that 5 plus -5 is less than or equal to 5 plus 4. So these wiring diagrams assemble together. So it takes the fact 5 is less than 6 plus 2, the fact 2 plus -5 is less than 0. This plus, by the way, is the tensor product. This is the order. And it takes the fact that 6 plus 0 is less than 5 plus 4 and combines them into the argument. It adds -5 to both sides of this. It reassociates the 2 and the -5. Why did it happen like that? Oh, I put things in the wrong order. If you do it in the right order, it works out nicely. So I'll go bottom to top. So we have 5 is less than 2 plus 6. 6, all right, top to bottom. 5 is less than 2 plus 6, so I add -5 to both sides.
So you have to do it on the same side.
-5 is less than or equal to 6 plus 2 plus -5. Then I reassociate here, so let's drop those parentheses. I take the 2 and the -5, and I say that that's less than 0 there. And then finally, for my third less than or equal to, I'd say that 6 plus 0 is less than 5 plus 4, and I get the whole argument. Okay. Okay, any questions about that? So that's what these wiring diagrams mean. So in this picture over here, it was like, if I know I can get yolk and white from eggs, and I know I can get meringue from white and sugar, and I know I can do all these things, then I know I can get a pie from crusts and whites and sugar and all that stuff. So it's the same story. And so my next topic is some examples from various fields. First, applied fields, and then math. And the applied fields kind of help you ground like where you could actually use this, maybe. And the math stuff is more like what we're going to use later in the course. I guess it depends if you're a mathematician or not, what you're going to actually use. Okay. So examples from science, etc. Science, manufacturing, informatics. So in chemistry,